Okay. All right. Obviously, the answer to the first one is either going to be A or B. I am hoping that it was pretty obvious. So I'm going to count to 3, and then I go 1, 2, 3, and then you're all going to answer simultaneously, and it'll be in unison because it'll all be correct. 1, 2, 3.
A.
Oh, I love you all. Perfect. All right. Now the question for number B, for the second one. 1, 2, 3.
B.
Yes, it's B. All right, because 1.3 plus 5.5 is less than 0.9 plus 7.12, even though you can just eyeball it, right? I don't know if you. All right.
So you expect it to be different than question 1, right? Because it's different answer.
Never know. I do a lot of randomness in my life for just that reason, because I feel like, but not here, obviously. Here I'm teaching because I can't do. I have to teach. Okay, after putting this node in the closed set, which is B, then what is the order of the nodes on the multi-map? Okay, 1, 2, 3.
C.
No. C, comma, A. C, A, yeah. Because C is going to go on there first, because C is definitely that, right? Because the path length to C, which is going to be 1.43 plus 1.72 plus its heuristic, is going to be less than A's path length plus heuristic. Is it?
Yeah, I got it.
Yeah, it is. Okay. Now the last one. Okay, which one's put on the closed set first? D or F? Here we go. 1, 2, 3.
D.
Oh, conflict. See, now if this were an English class, we'd talk about it. But it's not. It's a computer science class, so I'm going to say anyone who answered D is wrong. I'm just kidding. Are they wrong? The key is, all right, the whole key to answering this question is they're all coming from C, right? We can ignore everything before the graph. We only care about what's coming from C because it has to go through C. So let's just look at the path length from C plus the heuristic. So 2.83 plus 1.39 is going to be what? It's going to be 3.42. Is that right?
4.22.
4.22. Whereas this one is going to be 2.14 plus 2.06, which is going to be 4.20. So the answer is D.
I cannot.
So it's hard to eyeball it. You eyeball it might be F, but the answer is actually D because you have to actually do that math. How do we do? You going to make me feel good? Let's see how we feel. There we go. All right, well, that's good. 96. 96. All right, this one becomes more difficult.
Every note is there.
And then the last one, oh, look at that. All right, crowdsourcing got it right, as it often does. Okay, now, we've got 20 minutes left, and I'm going way too slow, but no one cares because no one cares. Because you don't need this for anything except for your own internal edification. It's academic. That's what academics should be, right? It should be divorced from anything practical.
Just for a bunch of geeks anyway.
That's right. And citation counts. Don't forget your citation counts. All right. Now, I wrote a program to do this because that's what I like to do. Obviously, I needed something to generate the J-graph. At some point, I'll tell you about the graph generation because it was actually really hard. Okay, so this was actually kind of fun. So here's my program. So up here, there's my program. I'm not going to go over it, but just look at the output, okay? The output of this program is the time, the path length, how many nodes got put in the closed set, how many nodes got put in the open set, and then how many nodes were unvisited. And I do Dijkstra and A star and some other stuff. And so just on this little bitty graph, right, you can definitely see how A star is superior. Again, you can look at the blue, and you look at that, or you can look at the numbers, you can see how the closed set size is different. Okay. So what I wanted to do is I wanted to make a better heuristic. Since Will wants a better heuristic, I decided I was going to make a better heuristic. And so my heuristic was, my next heuristic was for each node, my heuristic is going to be, I'm going to look at all of the edges, and I'm going to take the edge length to that node plus its heuristic, right? Plus its Euclidean distance.
Wait, what?
Okay?
Okay, plus its Euclidean distance or plus its heuristic? Because
Plus
then we're
it-
just going forever, right? So
Right, so it's going to be plus its Euclidean distance. Okay, although I could make it its heuristic.
Recursive heuristic.
I could. Right, so you'll know, right? So let's look at this path, this node, right? Its heuristic is that. Its actual path length is that, which is larger. What its heuristic is going to be is it's going to end up being this length plus this one's Euclidean distance. That's going to be bigger, right? But it's still smaller than the actual path length. Right? So that's my heuristic. So I hacked it up. I'm talking about graph generation. I hacked it up, and this is what I got. Now, go back and look at the A star. Look at how many blue nodes there are with my first A star right here. 2. See them? And I did this one. Now how many blue nodes are there? 5. But my heuristic is better. And I bring this up because this happens to me. This has happened to me multiple times in my life, right? I generated a result, and that result contradicts theory. So what's wrong, the theory or my program? It's my program.
I mean, is it better heuristic?
It is a better heuristic. You can prove it's a better heuristic. What I forgot, this is what happened in my code, I forgot to make this one 0.
Yeah,
So this one I
because-
turned its heuristic into path length to nodes plus their heuristic. And so in doing so, I made this node more unattractive than that node. Isn't that crazy? And I only discovered it because I looked at the picture. When I looked at the picture, I was like, oh, my code's not right. I just include that as a lesson. This has happened to me, I can tell you, probably 4 or 5 times in my computer science life, where by looking at stuff, I'm like, oh, something's wrong. And I avoid publishing something wrong or being embarrassed. So here's the real heuristic, and it is better by 1. Okay. I also hacked this up so that I would use H values that are too big. Now, what I forgot to tell you here is that when your H values are too big, then it might not find the shortest path. But it might be faster. It might put fewer nodes into the closed set. Yeah, Brian.
How are you finding the Euclidean distance if you're just given like a matrix of like distances relative to each other and not like
The XY coordinates?
yeah.
Oh.
Oh, okay, cool.
You really kind of need those XY coordinates to figure out the distance.
Was that previous graph, did that have XY?
Yeah, yeah, yeah. In this, when I generated nodes, I just generated random XY. At some point, I'll talk about the graph generation because it actually was algorithmically a difficult task. If I have time, I'll talk about it, but it's optional. So what I did here, now I want to make estimates that are too big. Oh, and if my estimates are way too big, like infinity, then it becomes a depth first search. So it's kind of nice that A star runs the gamut between Dijkstra and depth first search, which is neat. Okay, so H value is too big. What I do is I give this value here on this parameter is what I multiply the Euclidean distance by to make my H values too big. So here I multiply them by 1.1, and as it turns out, it finds the same path. Here, if I multiply it by 2, it actually finds this path. You'll notice that all nodes are in the closed set, but it finds the wrong path. But it will often find a path that's good enough for you. So
It's
yeah.
using the
No, it's using the original. Yeah. All right, and so now here are my pictures of big graphs. Right? So here's the graph. As I said, finding the yellow nodes is kind of like finding Waldo. There it is. Okay. Here's Dijkstra, visiting almost all the nodes. Here's A star, which, as you note, narrows that search. Here's A star with the improved heuristic down here. And if you look at the closed set size, oh, that was good. Okay. If you look at the closed set size, it is indeed smaller, right? 4816 versus 4893, but it actually is slower because of the extra calculation. Now when I make the factor 1.1, you'll notice my path length is now bigger. Right? All these other path lengths were the same at 30.706. When my heuristic is too big, it found a path that was bigger, but it was faster, and the closed set size was smaller. When I made the factor 2, now my path length is much bigger. Still pretty good though, right? And my closed set size is tiny. And it's kind of cool because if you look at this graph, you'll notice there's kind of this black tunnel right here. There's a barrier, right? And so it has to navigate the barrier. It's fascinating. I find this shit fascinating. So when if you look at the, here's my graph, J graph, right? Rotating the hash thing, right? Custom hash labels rotating, right? There's the running time. Here's the closed set size. It's close, but it's not exact, right? Especially because here the running time was slower, even though the closed set size was smaller. And then here's my path length. And so what you'll note, I mean, if you're writing a gaming app, it may well be that this point is totally sufficient, right? You don't have to get the exact closest shortest path, just something that's short, and it's so much faster. So that's cool. Did you have a question, Kelvin?
I was thinking just for like implementation actually out in the industry or something like this. Is this something similar to like what Google Maps would use?
I'm sure. I'm sure they use something like, they might use something better. Who knows? It's Google, right? But yes, Waze, you know Waze is doing this, right? And to Ku's point, I'm sure Waze pre-calculates them all so that if they have, when they're doing it on the fly, well, I guess you can't when you're dealing with traffic. If you're just doing a map, it would pre-calculate them all to make them fast. Okay.
If you were dealing with traffic, you could just add a second heuristic, right?
Yeah.
That's the traffic time?
Yeah. Oh yeah. Actually, I wouldn't add the second heuristic. I would just add my average time, my time. I wouldn't even do distance. I would just do time. Right? City Streets Lab. That's what we did. Those of you who had the pleasure of taking my class. Okay. But I'm not done yet. All right, this one came from my research. All right, so in I do AI. I hate AI. Okay, so fortunately, Dr. Schumann does most of the AI, and I just get to hack and do system stuff, which is fun. But this was one when this was during COVID. I was so lucky. I bought myself out of teaching the year COVID hit, the semester, spring 2020. I wasn't teaching, thank God, that semester. I was doing this. So, OpenAI Gym is a suite of applications that are meant for machine learning, okay? And they're for developing machine learning agents. And part of OpenAI Gym is a whole bunch of Atari games, old Atari games. And then what OpenAI Gym does, well, I'll talk about more later. This is one of them. This is called Freeway. You got these cars that are going back and forth in different ways. And you got a chicken, and the chicken's got to cross the road. And if it gets hit by the car, it gets knocked back a couple and freezes for time, so you don't want to hit the cars. Okay. And so then the goal is to develop AI agents. And what they do, actually a lot of the work that people do nowadays with things like this is they will actually take the bitmap of the screen, and that will be the input for their AI agent. So they got to do some deep learning to do some, to figure out what's what, and then they can do some reinforcement learning on it. We were just doing our standard genetic algorithm that we do. I'll talk about that someday. But in doing this, what I did, because I'm me, is back up. The other thing OpenAI Gym gives you, so Atari games, and this is fascinating. Atari games work on 128 bytes. That's their state, is 128 bytes. And that's like their memory of what they do. And then their application will do the graphics and stuff on the 128 bytes. But the 128 bytes is what the game state is. So chicken, cars, everything is represented in these 128 bytes. And a lot of AI agents, if they're not looking at the pixels, they look at the bytes. 128 bytes. That's your input. Can you figure out how to do good machine learning on that? Now our stuff you can't, because 128 bytes is way too much for our crappy genetic algorithm. Okay, so what I did was I went into JGraph, I ran this, and then I graphed each byte over time. And in doing that, I figured out which of the 128 bytes are the cars, had the X position of the cars, which of the 120 bytes are the Y position of the chicken. And I pulled those out. Now I'm going to do my AI on that because it's reducing the space and makes it a whole lot easier. So there's oh, that's the one that hit the projector. We'll do that.
That's recorded now.
No one is ever watching this video. It's okay.
It can be deleted.
It will be deleted. Okay. So now, I've got an AI agent which actually now only has like 11 inputs, which is I can deal with that. But then I had to ask myself the question, what's perfect? Right? What's the good player? And I was like, okay, I could write an oracle. I'm going to write an oracle that tells me you give me a seed, and I'll tell you what the optimal strategy is for the chicken. So what do? I turn it into a graph. I turn the chicken into a graph. And basically what I'm going to do is my graph is going to have two things on it. Y value of the chicken, time step. Okay? And, right, so now I have a shortest path problem. What is the shortest path from bottom, 0 time, to anything on the top? Right, my shortest path length, that's going to be my optimal chicken. What made this harder was the fact that the freaking graph wasn't deterministic. So this happened. As here are two different paths that the chicken can take to the spot 814, where its Y value is 8. I'm sorry, its time step is 8 and its Y value is 14. And two different paths. Then if I say, hey, chicken, go up, I actually got two different Y values. So that sucked. So what I did was instead, I wrote a program that would incrementally do this, and whenever it went to one of these nodes, it would always get to it the same way, so it could be deterministic. This took a while. It was in Python. I wrote a C wrapper around it, and so I could do it in C. So my A star pro. So now I have the shortest path problem. What's my heuristic? Well, my heuristic is what would be the minimum number of Y's if I wasn't going to hit a car? What's the minimum number of steps that it takes for me to hit the top? Perfect, right? It's an A star heuristic. And so then I wrote the code to do this. Now this graph's going to be enormous, so I'm going to do it on demand. I'm not going to generate all the nodes. I'm going to just run the A star calculation, and if a node's not hitting the multi-map, I'm not looking at it. I'm not generating it. Especially because every node actually had to do a Python call out. But here's the graph. Isn't this cool? This is the oracle that was done with A star, right? Of one of the seeds of the optimal chicken strategy, which was basically hang out, go, right? Go, stop, go. Right? It's pretty cool though, right? And you could see, right, whenever I had a collision node, I could stop. If I didn't have a collision node, then I'd have to generate all the edges. Right? So that was pretty cool. I can show you the perfect runs if you want. Maybe. It's a video. Oh, look at that. Hi. Oh, your dog is so cute. Okay. All right. So here's the oracle running A star. There's a better one. I like this one. This was a neural network that we actually generated, and I call this the scared chicken because it never collides, but it's like, oh no, back. I love it.
Wait, does it actually never collide?
Yeah, I don't think it might. I don't know. It might not. You can watch the video. It's, only 29 seconds, so who knows. Okay. All that shit's pretty cool. I thought that was pretty cool. That was fun. I wrote a paper and put it on the archive because I'm old. I've got tenure. I don't need to generate citation counts, but for this class I wanted to be able to cite it. So I actually did write a paper. It's published on archive, and it has a citation from like a medical journal paper. I kid you not. It's like, did that person read it? They couldn't have read this paper. Anyway, so this link here, let me just now tell you the last part of this. This link, and actually this link wouldn't be a bad choice of JGraph examples. Because you could animate. You could animate or show state of A star with all this. Anyway, I call this the Philadelphia Phillies puzzle. So when I was like 8, I'm from Delaware. I was a Phillies fan when I was growing up. My parents took me to a Phillies game. We went to the souvenir shop, and typical of my parents, they're like, here's $1. So I'm not getting a t-shirt, right? I'm not getting a hat. What do they have? They got a little plastic game with like a 4x4 grid where one of the squares is gone and you can slide them. And then if you get it right, it has the Phillies logo. So I got that, right? And then, I messed it all up, and then I was like, then I popped the pieces out so I could get it back together again, right? Because that was too hard. Well, in this link, they solve that problem using a star, saying, well, this is a graph problem, right? Every state of your squares is a node. Every edge is you sliding a puzzle piece, okay? So there are a lot of states to this graph. How do you make it a star? Well, my heuristic is how many squares are in the wrong place. Now, obviously, that it's perfect for a star, right? If I have 4 squares in the wrong place, it's going to take me at least 4 moves to get them in the right place. Now, it might take 15, right? But it's low, and it's a heuristic. And they use that as the heuristic to solve the problem. Isn't that freaking cool? I just think that's really cool. So that's an example for Will of a heuristic that's not Euclidean distance, but it passes all, and this one's kind of, that's close to Euclidean distance, right? Tops. But that one's not. That's fascinating. And they did. Okay. There, I got through A star today with everything. That was a good day. I love A star. It's a good lecture. All right. Enjoy Thursday. Do you know did I tell you who you're getting? Do you want to know, or you want it to be a surprise? If I tell you, are you still going to come to class? You have to, because I'll penalize you. Mars. He's going to teach you Rust. Yeah. He's like, I'll teach him SIMD algorithms. And I'm like, no, I want to teach him SIMD. And then I thought, God, what if he did a better job? That would suck. So no, he's doing Rust. All right.